Hello everybody, so in this video we're going to look at how to find limits of lots of different types of sequences. And there are going to be several different techniques. Some might be familiar from looking at functions, some might be new. So let's get started with the limit laws. So the limit laws are a way to combine two limits that we already know to find limits of other functions that are basically made up from them. So suppose an and bn are two sequences that we know converge to something, and c is a constant. Then we can say something about other sequences that we get from combining a and b in various ways. For instance, the limit of an plus bn is the limit of an plus the limit of bn, or the limit of a difference will be the difference of the limits. The limit of a constant times an is a constant times the limit of an, so we can bring the constant out. The limit of a product is the product of the limits, so we can just take the limit of each term separately in a product. The limit of a quotient or of a fraction is the fraction of the limits, so we can do the limit of the top divided by the limit of the bottom, provided the limit of the bottom is non-zero. We want to stay away from dividing by zero. And then lastly, the limit of a power is the limit to the power. So we can bring the limit inside a power. Here we have to assume that p is going to be strictly bigger than zero and the terms in the sequence should be also positive. For instance, we don't want to end up taking roots of any negative numbers and so on. And this also works with roots. For instance, if p is a half, then you would get a into the half, you will be looking at square roots. So this is for powers and including roots if you just look at fractional powers. Okay, so for instance, here is an example. Let's suppose we know that an tends to 9 and bn tends to 2. Let's look at this mishmash made up of an and bn in various ways. So we have the square root of an divided by 1 plus 3 bn squared. And we have several steps, so several different limit laws we need to use. If we just focus on the top for a second, if an tends to 9, here we have the square root of an, that's an to the power 1/2. And we said that we can pass the limit through the power. So if we take the limit through, we have the square root of the limit of an, and so we get the square root of 9. So the limit of the top is going to be the square root of 9, just bringing the limit through the power. And then the same idea for the bottom. So if bn tends to 2, then bn squared is going to tend to 2 squared, just passing the limit through the power. Then we multiply by 3 using the constant multiple rule. The limit of 3bn squared is 3 times the limit of bn squared. And then we have a sum of two different things. One is tending to 1, clearly. It's a constant sequence, we can think of it as. So this part's tending to 1, then we have a part tending to 3 times 2 squared. So the sum tends to the sum of the limits, 1 plus 3 times 2 squared. So this tells us the limit of the top and the limit of the bottom. And then lastly, the limit of a fraction is the limit of the top divided by the limit of the bottom. So this is going to be square root of 9 divided by 1 plus 3 times 2 squared, which is 3 over 13, which we were allowed to do because the limit of the bottom is 13, which is non-zero. Okay, so sometimes we might also need to use algebra before we use limit laws. For instance, if we end up with 0 over 0 or infinity over infinity, we're going to need to rewrite that so we can see what's happening. For instance, we look at 2n squared plus 3n plus 1 over 5n squared plus 6. If you just look at the top and look at the bottom separately without doing anything, the top's going to go to infinity, the bottom's going to go to infinity. There's not a lot you can say with the limit laws. But if we divide top and bottom by n squared, then we would end up with 2 plus 0 over n plus 1 over n squared divided by 5 plus 6 over n squared. Then the top is going to go to 2 and the bottom is going to go to 5. Then by the quotient rule, this is going to go to 2, or the quotient limit law, this is going to go to 2 divided by 5. So sometimes just rewriting using algebra enables us to use limit laws. Sometimes we might also need to think a little bit. So for instance, if we look at n over the square root of 10 plus n, the top goes to infinity, the bottom goes also to infinity. So we want to rewrite it. One thing you could do is to divide top and bottom by n. Then the top becomes 1. But if you divide by n and take that inside the square root, that becomes dividing by n squared. So we would get 10 over n squared plus 1 over n. And then if we look at what's happening on the bottom, on the inside, as n goes to infinity, that goes to 0. And then we have the square root of something going to 0 is going to go to still 0. And then we have a fraction where the top is 1 and the bottom is going to 0. And everything is positive. So that means that's going to go to infinity. Okay, so sometimes algebra combined with the limit laws is going to be all we need. But in other cases, we might need some other tools. For instance, the squeeze theorem is often useful. So often if we have a sequence that's kind of hard to understand, maybe it has sine or cosine, things that are alternating. One thing you could do is compare it to simpler sequences we already understand. So squeeze theorem says, suppose we have three sequences. We have a small function, a small sequence, a medium sequence, and a big sequence. And then if the limit of the small function and the big sequence are the same, so the limit of the top is equal to the limit of the bottom, then the limit of the middle, which is squeezed inside, is equal to the common value. So if the top and the bottom are both going to the common limit, to the same limit, then the thing in the middle has to go to that common limit too. It can't escape. It's kind of trapped by the two sequences. One consequence of this is that if the limit of the absolute value is 0, then the limit of a sequence itself is 0. For instance, the sequence itself is always trapped between the absolute value and the negative of the absolute value. So if we know the limit of the absolute value is 0, both the absolute value and the negative of the absolute value are going to 0, then the sequence is trapped and goes to 0 itself. For instance, the absolute value of minus 1 to the n over n, that would be plus 1 over n. 1 over n goes to 0, so that tells us that negative 1 to the n divided by n goes to 0. This is the sequence minus a half, this is the sequence minus 1, minus 1 plus a half, minus a third plus a quarter, and so on. Okay, maybe a more interesting application of the squeeze theorem is if we look at things with sign inside. So sign of anything is always between minus 1 and 1. So if we look at sine of n squared divided by the square root of n, sine of n squared is less than 1. So sine of n squared divided by the square root of n is less than or equal to 1 over square root of n. And sine of n squared, doesn't matter what's on the inside, sine of anything is always bigger than minus 1. So this is bigger than minus 1 over the square root of n. And now both of these functions on the left and on the right are going to 0. For instance, as n goes to infinity, square root n is going to infinity, 1 over that is going to 0. And sine of n squared divided by square root n is trapped between those two. So it must also go to 0. Okay, so this is a classic example of squeeze rule, or squeeze theorem. Okay, maybe another example is, does an equals n factorial divided by n to the n converge or diverge? So remember, n factorial is a product of the first n whole numbers. So these, clearly both the top and the bottom are huge numbers, right? N factorial is huge, n to the n is huge. So we're going to have to understand what's going on because it's infinity over infinity. And n factorial does not come from a function. So you cannot use L'Hopital's rule or anything like that. So we have to use a comparison or the squeeze rule. So one thing you could do is to write out all the terms. So remember, n factorial is 1 times 2 times 3 up to n. It's the product of the first n whole numbers. Whereas n to the n is just n copies of n multiplied together. So it's n times n times n times n, n times, and so on. So if we write out all the terms, we see we have this expression. And then one way to think about it is if we look at each pair. So rather than thinking of it as 1 times 2 times 3 up to n divided by n times n times n up to n, we could think of it as 1 over n times 2 over n times 3 over n up to n of n, and so on. Think about it that way. And then a trick here is to split off the first term, which is 1 over n, and then everything we're left with is 2 over n, 3 over n, up to n over n. And then every term in this product is less than 1. For instance, 2 is less than n, so 2 over n is less than 1, 3 over n is less than 1. Finally, n over n, the last term, is equal to 1. So everything here is less than or equal to 1. So 1 over n times something less than or equal to 1 is less than or equal to 1 over n. So that's where the 1 over n comes from. Okay, so lastly, what do we get? So clearly everything is positive. It's a positive sequence. We showed that 0 is less than or equal to an is less than or equal to 1 over n. And we know that 1 over n goes to 0. So the sequence is trapped between 0 and something that's going to 0. The limit of an is going to be equal to 0. Okay, so this is another common application of the squeeze rule or the sandwich rule or whatever people call it. Okay, another common trick is we can take limits through continuous functions. So if we have a sequence and then we get a new sequence by applying a function to it, say, I start with the sequence an and I apply f of x equals x squared, I will get an squared. Or I start with the sequence an and I apply e to the x with it, I will get e to the power of an. If I get a new sequence in that way, I can find the limit of it by bringing the limit inside the function, provided, so this is a helpful way to think about it, the limit of f of an is f of the limit of an. So I can bring the limit inside the function, provided the function is continuous at the limit point, and that part is important. So here are some positive examples. Say we want to find the limit of sine of pi over n. Right, sine of pi over n is a perfectly good sequence. Right, there is the first term, sine of pi over 1. Second term, sine of pi over 2, sine of pi over 3, sine of pi over 4, and so on. It's a sequence. We can find the limit of it by taking the limit inside sine. So the inside is pi over n. That tends to 0. So the limit of sine of pi over n is going to be sine of 0, which is 0. We just bring the limit inside, do sine at the limit, because sine is continuous. Same story, we'd say e to the 1 over n plus 2. Right, we can bring the limit inside because exponential is continuous. The limit of 1 over n plus 2 is 0 plus 2, which is 2. So the limit of e to the power of that is going to be e to the 2. Say we had ln of n squared plus 5n plus 1 over n squared plus 2. The inside tends to 1. For instance, we're looking at the highest powers of n squared, dividing both top and bottom by n squared, you would see the limit is 1. If we want to do the limit of ln of this, we pass the limit through. It will be ln of the limit, that's ln of 1, which is 0. Okay, let me make the warning that I said continuity is really important if we want to bring the limit inside the function. So here is an example where things go wrong if we don't have continuity of the function. So let's suppose we have f of x is 0 when x equals 0 and f of x equals 1 for x not equal to 0. So it's 1 everywhere away from 0 except at 0 it's 0. This is a non-continuous function, right? If I approach 0, if I approach x equals 0, I'm always going to have value 1 until I actually get to 0, and then very suddenly it jumps to value 0. So this is a non-continuous function. And let me look at the simple sequence an is 1 over n. And let's compute two things. Firstly, if we look at the limit of f of an, okay, so what is f of an? Well, an is 1 over n, which is clearly non-zero. So the value at 1 over n is going to be 0. For instance, the value at a half is 1, the value at a third is 1, the value at a fourth is 1, and so on. The function values away from 0 are always 1. So in this case, f of an is going to be 1. We have the limit of 1. That's just 1. But then if we look alternately at f of the limit of an, if I put the limit inside, the limit of an is 0. 1 over n goes to 0. So I would end up with f of 0, and f of 0 is 0. So clearly 0 is not equal to 1. So the limit of f of an is not f of the limit of an. So in this case, we cannot bring the limit inside. That will give us the wrong answer. And as we said, what goes wrong here is that the function is not continuous. So please check make sure the function is continuous before you apply this trick. A lot of the functions you see are continuous, but there are some non-continuous ones out there. Okay, next up, we finally have geometric progressions, which are an important type of sequence, and they're going to be an especially important type of series when we get to looking at series. So if r is if r is just some constant, then the sequence r to the n is called the geometric progression with ratio r. And different r's are going to give different sequences. So here are some examples. If r is 2, we get the sequence 2 to the power n. So if we plug in n equals 1, we get 2, n equals 2, we get 4, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and so on. Or if we pick r equals a half, we're going to have the sequence a half to the n. So if we plug in n equals 1, 2, 3, and so on, we're going to get a half, 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the 4, 1 over 2 to the 5. We just do the different powers of r. Or we could have, r is negative a third, then we would do the different powers of negative a third. Negative a third to the 1 is negative a third squared is 1 over 9, negative a third cubed is negative 1 over 27, and so on. So geometric sequences just look like r to the power n. As n gets larger, we take higher and higher powers. We multiply more and more times. Okay, so we need to know what are the sequences of these, are the limits of these sequences. Clearly, they behave very differently, right? If r is 2, clearly this one is going to infinity. If r is a half, clearly this one is going to 0. And if r is minus a third, well, this one is alternating in sign, but it's still going to 0. It doesn't matter that it's coming from two different sides. Okay, so when does this sequence converge? It converges if r is strictly bigger than -1 and less than or equal to 1. So the geometric sequence converges for -1, strictly less than r, less than or equal to 1, and it's divergent for all other r. If it's convergent, then if r is strictly between -1 and 1, then it converges to 0. For instance, as we saw with r equals a half and r equals negative a third. And if r equals 1, then it will converge to 1. Now, let me spend maybe a moment or two just talking about the endpoints. So why are the endpoints different, -1 and 1? If you were to pick r equals 1, then r to the n just becomes 1 to the n. It's just 1. It's just 1, 1, 1, 1, 1. All the entries are 1. Clearly, the sequence converges to 1. Whereas if r is equal to -1, we would end up with -1 to the n. It's going to go between -1, -1 squared is +1, -1 cubed is -1, -1 to the 4 is +1. It's going to alternate between -1 and +1. So it will not converge. So that's why we have the different behavior at the endpoints. Okay, so for example, we can combine these with the limit laws and other tricks. For instance, if we were to look at 4 to the n divided by 1 plus 3 to the 2n. So the geometric sequence looks like r to the n. So if you have something that looks like something to the 2n, then you're going to want to simplify that using the formula x to the a all to the b is x to the ab, the exponent rules. So we can think of 3 to the power of 2n as 3 squared all to the power of n. 3 to the 2n is the same thing as 9 to the n. Okay, so now it looks more like a geometric sequence. And now we have something that goes to 0 to infinity on the top, something that goes to infinity on the bottom. So we are going to want to rewrite this in some alternate way. For instance, we can divide top and bottom by 9 to the n. If we divide top and bottom by 9 to the n, we get 4 over 9 to the n divided by 1 over 9 to the n plus 1. Now we have two geometric sequences with ratio -1 less than r less than 1. If, right, 4 over 9 to the n is going to go to 0, 1 over 9 to the n is going to go to 0. We have something that goes to 0 divided by 0 plus 1. That's going to go to 0. Okay, so these were various tools that we have for finding limits of sequences. Some are similar to functions, some are not. And then we finish with an important sequence, which is the geometric sequence. Looks like r to the n. Thanks, everyone. See you next time.